So we've talked about Newton's first law, we talked about Newton's second law. Now it's time to talk about Newton's third law. And again, most people would say that Newton's third law is for each action there's an equal and opposite reaction. And so just to be clear, in Newton's language, action and reaction, both those words meant forces. So for each force, there's an equal and opposite force, is the way that we tend to generally think of Newton's third law. So let's sort of put this into practice then. So I've got a box of mass m that rests on a horizontal surface. The question I'm interested in asking is, are the weight of the box and the normal exerted on the box by the surface a Newton's third law pair? So I'm going to encourage you to pause for a second here, think about this, come up with an answer, then press play again. All right, well, it happens that no, these two are not Newton's third law pairs. So even though they are clearly both forces, they have the same magnitude, they point in opposite directions, they do not constitute a third law pair. So we want to understand why that is. So for starters, Newton's third law, as we tend to think of it, is missing some important details. So just like we talked about with Newton's first law and Newton's second law, kind of our common phrasing of it misses some really important information. So sort of the more accurate way to think of Newton's third law is that for a force that object A exerts on object B, there is a force of the same type that has the same magnitude but points in the opposite direction that object B exerts on object A. So if we wanted to, a more complete way to sort of denote the forces within a free body diagram would be to indicate not just what type of force it is, but which object it acts on and which object is the one causing the force. So the more complete notation might be F type on by. So as an example, you might talk about the gravitational force exerted on object 1 by the Earth. And so if we were to think of the two forces in this example here, we have two of them. One is the normal force, the other is the gravitational force. Both of them act on the box, which we'll choose to call object 1 in terms of the labeling here. But notice that they're caused by different secondary objects. So the normal force is on box 1 and caused by the surface. The gravitational force is on box 1 and caused by the Earth. So to be a Newton's third law pair, the important detail is, or one of the important details, the two that we tend to miss, is the type of force needs to be the same. That's a normal force, that's a gravitational force, not the same type of force. And then the indices for on and by need to switch. So if you think about the rules that a pair of forces must follow, if they're going to end up being a third law pair, there's four things. The two that we know, the two that we sort of most commonly know, are equal in magnitude, opposite in direction. But the two important details that we tend to forget are that they have to be the same type of force, and that the object which feels the force and the object which causes the force are reversed in your third law pair. So if we want to think about the Newton's third law pair for the gravitational force on box 1 by the Earth, that's a gravitational force, but it's the gravitational force on the Earth by box 1. This is not a force we tend to think about, but as much as the Earth pulls box 1 down, box 1 pulls the Earth up with an equal force. So the gravitational force that box 1 exerts on the Earth points up, so it's located in the free body diagram of the Earth. It's equal in magnitude to the weight of the box, and that's the Newton's third law pair for the gravitational force exerted on the box by the Earth. If we want to think about the gravitational force, the Newton's third law pair for the normal, Well, again, that needs to be a normal force. It will point down, but instead of being the normal force exerted on box 1 by the surface, now it's the normal force exerted on the surface by box 1. So in the same way that the surface holds the box up, the box pushes down on the surface. So that normal force, so the Newton's third law pair for the normal on the box is how the box pushes down on the surface. That's also a normal. That force would be located in the free body diagram of the surface. It's equal in magnitude to the force exerted on the surface, or exerted on the box by the surface to hold the box up. That's my Newton's third law pair piece. And then if I think about Newton's second law here, again, because I know that the two forces acting on the box cancel out, that means that that normal force, how hard the box pushes down on the surface, happens to also be equal to the weight of the box. So we want to make sure, one of the really important things to recognize is that because of this last rule, that the object which feels the force and the object which causes the force have to be reversed. Newton's third law pairs of forces can never be in the same free body diagram. They have to be in two different free body diagrams because the object which feels each force within your third law pair is different.